Empirical and molecular formulas. So as we get into this next topic, there is one major calculation that we've already looked at that I want you to keep in mind, and it is this: N, the amount in moles, is equal to the mass of a sample of a substance divided by its molar mass. So this should be a formula that's familiar to you from our second topic, relating mass, moles, and number of particles. So if you have that on a cue card or somewhere nearby, please just make sure you've got that as we go through today's calculation. So we're not really introducing anything new. We're just going to keep working with this formula. So please make sure you know what little n, little m, and big M stand for. And if you don't at this point, please go back and watch the previous videos before kind of forging ahead on this topic. So we need to know this formula. And then the second thing that we need to have handy, tool that we need to have handy, is a periodic table. And we're going to use that to help us determine molar mass, which, hint, hint, is what the capital M stands for. So two big things, tools in our toolbox here is this formula and the periodic table. Okay, I'm going to start with just a picture of three different molecules. So these are covalent compounds. All of them contain carbon, hydrogen, and oxygen. So if you remember when we were in class working with the model kits, carbon is represented by a black sphere or black atoms. Oxygen is represented by red atoms, and hydrogen is represented by white atoms or spheres. So here I have three molecules. What they have in common, I can tell you so far, is they're composed of the same three elements: carbon, hydrogen, oxygen. Okay, this first molecule is methanal, or what we commonly refer to as formaldehyde. So we have this lovely picture of a preserved specimen, a frog that was probably stored in formaldehyde or a mixture of formaldehyde and some other substances that we call formalin. Okay, the second molecule that I have here is acetic acid. Very, very, very dilute solutions of acetic acid, watered down acetic acid, are what we commonly come across as vinegar. And then the third molecule I have here, the biologists in the room may recognize this. This is glucose, so C6H12O6. And glucose is the major energy source to power our cells, and we find it sometimes in compound with other small sugars to make things like table sugar, but this is glucose. So I want you to pause this for a moment, and I want you to think about, just take a good look at this and see, is there anything other than the fact it's carbon, hydrogen, and oxygen, anything that these three molecules have in common? The other thing, I guess my little hint as you start to ponder this, proportions. Proportions. So pause your video here, take a look. Is there anything they have in common? Okay, now that you're back, turn this back on. It's the simplest ratio. So if I were to look at the number of carbon atoms, hydrogen atoms, and oxygen atoms in each of these three molecules, they all have the same simplest ratio. So in the first one, there's one carbon, two hydrogen, and one oxygen. That's in formaldehyde. And that's how the molecule actually exists. Now, if I look at my next molecule, acetic acid, you'll notice there's two carbons, four hydrogens, and two oxygens, C2H4O2. But if I were to simplify that ratio, oftentimes we don't do this, when we have molecules, because we want to show how many actual atoms are present, but the simplest ratio of the elements in that compound is one carbon to two hydrogen, to one oxygen. And then if I were to look at glucose, C6H12O6, 6 to 12 to 6, the simplest ratio of carbon to hydrogen to oxygen would still be 1 to 2 to 1. So what we can say that these three compounds, these three molecules have in common is the simplest ratio of their elements. And this simplest ratio is what we often refer to as the empirical formula. Think of it like the simplest formula. So in a molecule of methanol, or formaldehyde, The simplest ratio is also the actual formula for the molecule. In the case of acetic acid, the simplest ratio is 1 carbon, 2 hydrogen, 1 oxygen. Then the molecule itself actually has twice as many atoms. And if I were to look at glucose, the simplest ratio is 1 carbon to 2 hydrogen to 1 oxygen, but the actual molecule itself contains 6 times as many atoms, C6H12O6. So what we're going to do today is look at how you can determine the simplest ratio of elements in a compound, both covalent and ionic, which is essentially what we call the empirical formula, simplest formula. Okay, so when we talk about empirical formulas, we also should define what a molecular formula is. So I want you to consider 2 compounds. One is sodium chloride, NaCl, which we know as an ionic compound, a metal and a nonmetal. And then let's consider hydrogen peroxide, which we know is a covalent compound, groups of nonmetals, or they're sharing their electrons. So these are the 2 chemical formulas, how we can identify the types of elements and what ratio and how many, in the case of covalent, how many atoms there actually are in the molecule. So when we look at chemical formulas, they can either be stated in their simplest form, aka the empirical formula, or they could be stated as the molecular form, which is basically telling us how many atoms are actually in the molecule. Now, when we look at ionic compounds, and we mentioned this in our first unit, ionic compounds are always expressed in simplest terms, or the simplest ratio of cations to anions. So they're always giving you the empirical formula. So for something over here like NaCl, if I look at this little sample of salt, this ionic compound, for every 1 sodium, I have 1 chloride ion. Now I look in the sample, there's way more than just 1 of each, but what we've stated is the simplest ratio, the reduced ratio of 1 to 1. I don't think that's anything too new. And that was kind of our basis behind when we do like the crisscross rule, and then we simplify the formula. We always write it in its simplest form. So ionic compounds are always written in their empirical form, empirical formulas. Now I'm going to look at a covalent compound, however. So let's look at something like hydrogen peroxide. So it has the formula H2O2. With this compound, I could write down its molecular formula, which is telling me precisely how many atoms of each type. And this is telling me there's 2 hydrogens and 2 oxygens. If I wanted to report the empirical formula for this, we're going to do something that we don't, previously we didn't do. We didn't cancel out or reduce our subscripts. But essentially, the empirical formula is telling me that for every 1 hydrogen, there is 1 oxygen. Now, the problem with this, if I try to draw just a hydrogen and an oxygen together, if you tried to draw like a Lewis structure for this, you wouldn't be able to successfully complete it. You wouldn't be able to create a full octet. But that doesn't really matter. Empirical formula is just telling us the simplest ratio. But it's not really how the molecule itself exists in nature or in reality. Okay, so I've got a few examples here. Try writing the empirical, in other words, the simplest ratio for each of the following molecules. Now you have your worksheet that you could follow along with and try this, and here are the answers below. So if I were to look at propene, a really great fuel, I have C3H6. That's its molecular formula. There's 3 carbons and 6 hydrogens in the molecule. If I wanted to write it in its simplest form, or in other words, its empirical formula, I'm just going to simplify this ratio. Or I'm going to think of it this way. What's the biggest number I could divide both 3 and 6 by to get the simplest whole number ratio? So you might look at that and say, 3 to 6, that's the same as saying it's a 1 to 2 ratio if I divided everything by 3. So over here, my empirical formula for propene is CH2, the simplest ratio. Okay, let's try ethine or acetylene. That's the one, the little bomb I made in class, and you guys kind of blew up in your test tubes. C2H2, that's its molecular formula. In a molecule of acetylene, there's two carbons triple bound together, and then there's two hydrogens attached. But the simplest formula, or the empirical formula, the simplest ratio, 2 to 2, is the same as saying it's 1 to 1. So I would say its empirical formula is CH. Okay, continue on. Glucose, C6H12O6. That's how the molecule truly exists. But if I just wanted to state the simplest ratio, divide everything by 6. It's 1 to 2 to 1. And then for octane, C8H14, excellent hydrocarbon fuel. Let's divide by the biggest number we can. What's the greatest common factor we could divide these by? I would say, it's not going to be 8. How about by 2? So if I divided that by 2, my 8 to 14 ratio simplified becomes a 4 to 7 ratio. Okay, and the next question, can we identify each of the following? I'm going to give you the formula as being empirical. So is it a simplest ratio? Is it a molecular formula? Or in some cases, could it actually be both? So let's use the example of water, H2O. Okay, we know water exists as a molecule with two hydrogens bound to an oxygen. So that is its molecular formula. And the simplest ratio is 2 to 1. Can I simplify that any further? No. So in this case, for water, it's both its empirical and molecular formula. So I've stated that as both. Okay, my next molecule is butane, C4H10. That's the molecular formula, and I can identify this because take a peek, could I simplify that? And if you could, you said, yeah, that 4 to 10 ratio, why not decrease that to a 2 to 5? That tells you that no, it's not in its empirical form, so it must be its molecular form. So in a molecule of butane, you have 4 carbon and 10 hydrogen. The next one, CH. That is definitely a simplest ratio, 1 to 1. So that's empirical. Could a molecule exist like this? That's where it gets a little bit trickier, but if you were to try and draw one carbon attached to one hydrogen, try to draw the Lewis structure of that, it's not going to work. You don't have any molecule that can actually exist with just a single carbon and hydrogen. Some of your carbon electrons would still need to be paired. So in this case, this is an empirical formula. It's the simplest ratio, but a molecule can't actually exist as that. It wouldn't be stable. So it can't be the molecular formula. Then for my last one, I have a metal and a nonmetal. It's ionic. So it's always going to be empirical. It's always the simplest ratio. It can't have a molecular formula because sodium chloride's ionic. It's not actually a molecule. So as soon as you see something's ionic, we know that it has to be the simplest form or simplest ratio. Okay. Now, in order to find a simplest formula like CH or CH2O or NaCl, in other words, we're trying to find the simplest ratio of elements. What we're going to do, we're going to go back and use the formula that we've been working with before, which is moles. To find moles, we're going to use the mass of a sample divided by the molar mass. And in particular, if we know the percent composition, in other words, what elements the compounds are made of, we can use this to help us create a molar ratio of elements. So I'm going to work through a couple examples. Here's the question. Let's say we have a compound and we have determined its percent composition by mass. So after analyzing perhaps a sample, we find that 69.58% of the compound's made of barium, 6.090% is made of carbon, and 24.32% is made of oxygen. Okay, there's our 3 elements. What's the simplest or empirical formula? In other words, what's the simplest ratio of elements? So we know that there's only these three. What we're going to do, rather than leaving them as percentages, we're going to change them into molar amounts and compare how many moles we have of each. So there's 4 steps that we're going to follow each time we do this. Maybe, again, if you want to use a cue card and write out these steps to help you, you can keep them nearby to help us create these ratios. So step 1, what I want you to do, if I know the percent composition, I want you to just imagine you have 100 grams of a substance. So if I had a 100-gram sample of this unknown compound, and I said that 69.58% is barium, if it was a 100-gram sample, that means that 69.58 grams would be barium. In other words, I can just take the percentage and change it into a mass in grams. You're going to find that some of the practice questions, some that you'll see, will give you the mass in grams right off the hop. So you don't even really have to consider a 100-gram sample. But what we're going to do, if you're given a percent composition, let's just take the easiest number we can and presume it's out of 100. Then what we're going to do is for each of the elements in our compound, we're going to compare the amount in moles. It's not really fair to just compare the masses of the elements individually because all of them have different molar masses. So we want to report how many moles we have of each. And we're going to use that formula that we've used before. Take the mass of that particular element and divide it by its molar mass. After we find out how many moles we have of each, we're going to try and create a very, very simple ratio by dividing by the lowest number. And we're going to write that simplest ratio was what we call a mole ratio. Okay, so let's go through our example here. And now this is just going back to the percentages that I had before. So I'm just going to flip-flop back and forth to the question. You're going to notice for this, I'm not going to put really a given and a required list because, well, you can still put it, but I'm just going to hop right in at the calculation because really what I'm going to be doing is repeating the same calculation over and over just for each of the 3 elements. So I knew that I had, in a 100-gram sample, 69.58 grams. I'm going to take that and divide it by the molar mass of barium, just a single Ba, and I'm going to find this on my periodic table. So look up barium, and there it is, 137.33. I'm going to make sure I've included my units, grams for the mass and grams per mole for the molar mass. And then when I divide it, I'm going to keep at least 4, maybe even 5, if you're feeling like it, at least 4 digits to tell me how many moles of barium are in that sample. Then I'm going to do the same for my carbon. So I took my percentage, assumed it's out of a 100-gram sample, changed it into a mass in grams, and then here I found the molar mass of carbon. Calculate my value in moles. And then finally, I'm going to do the exact same thing for oxygen. So notice it's the same formula over and over. And if you had any difficulty kind of with our second topic, you are going to get sick of dividing mass by molar mass, but you'll definitely know how to do it by the end of this unit. And I'm going to take my mass of oxygen. It was 24.32%. We'll just presume it's out of 100, change that into grams. And then there's the molar mass of oxygen. So here's my ratio. I have 0.5066 moles of barium, 0.5071 moles of carbon, 1.520 moles of oxygen. So if I wanted to write out my formula, my simplest formula, here's what my subscripts would look like. When I look at that, that looks hideous. We never see formulas that have decimal values or fractions as our subscripts. We want to give a nice whole number ratio. So the last step, what I'm going to do is take the smallest number out of the 3 that I have, out of the mole values I've calculated. So the 0.5066, I'm going to divide everything, each of these subscripts by that. So when I divide that by itself, my subscript, I know I'm not showing it here, but it basically becomes a 1. Okay. This one, when I divide by 0.5066, it's pretty close to 1. And when I take 1.520 divided by 0.5066, that's pretty close to 3. So this ratio, as ugly as it is here, can be very nicely written as a whole number ratio of 1 to 1 to 3. It's kind of like saying 0.5066, 0.5071, 1.520 is the same as 1 to 1 to 3. We're just going to put it into a whole number. And therefore, we can find the empirical formula, the simplest ratio of elements for this compound, which is BaCO3. In other words, we've determined, after looking at the percent composition, that this unknown compound I was working with is barium carbonate. Okay, I'm going to give you another example. I want you to try working through this exactly the same way that we did with the previous one. Okay, so at this point, it might be a good chance to just kind of pause, try this on your worksheet or on your note, and then see if you come up with the same answer. So pause it and then come back when you're done or when you're stuck, and we can check against it. Okay, and now you're back. So I have a compound. Here's the percent composition. Remember, that just means the percent of every element. Find the empirical formula. The simplest ratio of elements is a molar ratio. So what I'm going to do here is find moles of sodium, moles of sulfur, and moles of oxygen. And I'm using mass over molar mass as my formula each time. Since I've been given a percentage, let's assume a 100 gram sample. So then I'm just going to take all of my percentages and write each of those as a mass in grams. The molar mass, what's the molar mass of sodium, of sulfur, and of oxygen? I'm getting those directly from our periodic table. And then let's calculate how many moles we have of each. There we go, there we go, there we go. And before I even go any further with this, I'm going to look at these first two and say, whew, those are pretty close. Okay, let's write out our ratio. For every 1.266 moles of sodium, there's 1.263 moles of sulfur and 1.900 moles of oxygen. There's my ratio. It doesn't look great. Let's divide by the smallest value you have out of those subscripts, the smallest molar value. 1.263. So when I divide each of those three values, I then get a 1 to 1 to 1.5 ratio. Now that looks pretty good, except I still don't really love that 1.5. So let's stop and think, is there a way that we could get rid of that 1.5 and turn it into a whole number? Well, even though we've gone through and divided, maybe now we're going to multiply. What's the smallest thing I could multiply 1.5 by, 1.5 by? Well, if I doubled it, that gives me 3. So the simplest ratio with whole numbers, I'm going to take this 1 to 1 to 1.5 and double to 2 to 2 to 3. And now we have an empirical formula for our compound, which gives us the simplest ratio of elements. Okay, so all the same steps that we saw before. The little twist with this one is after we divide, we still have a decimal, so maybe we can multiply that out to get rid of it. Give us a nice whole number ratio. Okay, I've given you another example here where the information about the compound isn't given in percentage, rather it's already expressed as a mass in grams. This is why I mentioned before, this means you just simply don't have to assume it's out of 100 gram sample. We're just going to take the masses as we see them and let's start plugging them in. So let's find out, after we've analyzed this compound, how many moles we have of each. So carbon, hydrogen, oxygen, I've just plugged in my masses from the question. The molar masses, let's find those for each of the three elements from the periodic table. Let's divide these out. It's, as I said, it's not fair to just compare the mass you have of each element because the size of those atoms are very, very different. So we're going to account for molar mass and that differing size by converting it all into an equivalent unit, which is the mole. Here's our ratio. We can write that as our subscripts, but again, doesn't look wonderful. So let's divide by the smallest value to see if we can get a whole number ratio. So with this, I get a ratio of 1 to 2 to 1, which is the simplest formula or the empirical formula for the compound. I'm going to stop it here just to maybe consider the CH2O. If we went back, way back to the beginning, right here I have 3 different molecules that all have the simplest formula CH2O. They're very, very different though in terms of the number of atoms. So when we found the simplest or the empirical formula, we've just given the simplest ratio, but sometimes with covalent compounds, that's not enough information. Could you tell me whether this was formaldehyde? Is it glucose? Is it acetic acid? Ribose has the formula C5H10O5. There's lots and lots of different molecular compounds, covalent compounds, that may share the same simplest ratio or the same empirical formula. So our last little tack on to this is in the case for covalent compounds, sometimes you don't really know the identity unless you're told a little bit more information. So let's say I found a compound to have the empirical formula, simplest ratio CH2O. I'm then told, and you'd have to be given this additional information, that let's say the mass, the molar mass of the molecule or of this compound is 150 grams per mole. That additional little bit of information is going to help us determine how many actual carbon, hydrogens, and oxygens you'll find in the molecule. So what you're going to do is if you know the simplest formula or empirical formula, let's say like CH2O, let's figure out what its molar mass is. Let's assume I just had 1 carbon, 2 hydrogen, and 1 oxygen. So add up a carbon, 2 hydrogen, and oxygen, and you'll find that 30 or 30.03, I think if I kept a couple decimal places, would be its molar mass. Okay, but then I'm told that the compound has a mass not of 30 grams per mole, but 150 grams per mole. How many times larger is that? Some of you might be able to eyeball it and say it's 5 times the size. Some of you, maybe you want to double check. So I'm going to take 150 divided by 30. This is all very rough work. I dropped some units here. Bear with me. So 150 divided by 30 is 5 times as much. So what that's telling me is that in the molecule itself, there's 5 times as many atoms of each atom as compared to its simplest ratio. So what I've done, if this is CH2O is the simplest formula, empirical formula, and I know the molecule has a mass, a molar mass that's 5 times as much, I've just multiplied each of my atoms, number of atoms, by 5. So 1 times 5, 2 times 5, 1 times 5. And that means that this molecule actually exists with 20 atoms. Or we could identify this possibly as ribose, which is a sugar you might find in RNA. Okay, so I'm going to give you one last example. So I'd ask that you pause it here, try this out. The first portion of this you're able to do. So let's say we take a compound and we're going to burn it and we find out its composition, carbon, hydrogen, oxygen. Okay, what I want you guys to do, this is all using the same steps that we've just done with the previous couple examples. Can you find your carbon, hydrogen, and oxygen ratio? Okay, pause it, see if you can calculate this. Mass divided by molar mass. For some reason, I lost my grams in here. I apologize. Tisk, tisk. Let's add those back in. And then I want you to check and see if you get the same ratios. Okay, so pause it. And now you're back. Okay, so hopefully you had an empirical formula after you've tried that, took a few minutes to do it, of CHO2, simplest ratio. Now, one added piece of information in this question. We found the simplest ratio. Now I'm told the molecular mass or the molar mass of the compound is 90 grams per mole. Let's figure out its molecular formula. Maybe it's CH2O or maybe it's something bigger. So what I've done here, I found the molar mass of CHO2. Sorry, it went on to another line, and it's 45.02 grams per mole. I'm told that the actual molecule has a mass of 90 grams per mole. That's about twice as big just by eyeballing this. But if I wanted to be really sure, I could divide my compound's molar mass by the simplest formula's molar mass. And I find that it's about twice as much. So if I know my simplest formula, I know the molecule has twice the mass, or in other words, twice the number of atoms. All I've done here is doubled the amount of each element in my compound. Okay, so what we've done with this, we've used one formula, mass divided by molar mass. We have used information, so we're just flipping back through. Here it is. We've used our periodic table to help us find molar masses. We've used some percent composition to help us determine what the ratio in moles of each element is in the compound. Okay. What we're trying to do with each of these examples is find the simplest ratio of elements. And we're writing that now as subscripts to represent the moles that we have, the molar ratio for each of the elements. That is determining what is called the empirical formula, or the simplest formula for the compound. And in some cases, you may be given a little bit extra information that can help you determine what a molecule with a molecular formula actually may be. Okay. So if you have questions, I will be on the Meet. Please, please, please try these yourself before just kind of checking through my answers. If you hadn't done that, go back, cover up your answers, see if you can complete these on your own. And then please, as I said, let me know if you have any other questions. Thank you.